Okay, good morning everyone. Welcome to Wednesday of a very busy week 2. I don't know how your week 2 is going, but mine has been horrendously busy. Unfortunately, we have in our course forum tutors waiting to answer your every question about the course. So please don't email me. You'll be one of the many people waiting for an email reply from me if you do. Students, staff members, whoever. I'm not keeping up with my email, but because we know you need help and you need it now, the course forum is there for you. Alright, a big welcome to anyone who's joined the course since yesterday or this week. We've still got a couple of people coming in late. Last week's lab is not due until Monday, so you can go back to last week's lab exercises and you can watch the tute question, read the tute questions. You got anything you need to know, ask in the forum. Last week's lab is revision C. Submit last week's lab by Monday. Well, that applies to everyone. We'll try to get a reminder email going soon that gives you a heads up 24 hours out from submission deadlines that you haven't submitted anything. And of course, as well as last week's exit lab exercises, the other thing that's coming up due is this week's lab exercises, and things are winding up pretty fast. There's a lot in this week's lab exercises, so it's your chance to really we've only just seen bit operations, but this week's lab exercises is all about practicing bit operations, ripping apart integer values with bit operations to get bits of them, and putting things back together again. And there's some challenging exercises and some very challenging exercises with the lab exercise, and you get to play with an interesting and almost obsolete. I think there are binary coded decimal format it's a lovely venue for you to practice bit operations. Not seeing nearly as much use as it did some decades ago, but I think there are still people using BCD out there. All right. So today, what will today be? We've got to finish off a bit more about bit operations, and then we'll move on to floating point numbers, a really great topic. And we're going to use bit operations to dismantle floating point numbers and see how they're made. And in next week's lab, we'll get you to use bit operations to play with some floating point numbers. So let's finish off the conversation. I want to recap a bit about bit operations. There's 2 examples I want to do. One is sort of really important core stuff, and that's the Pokemon one that's on my screen right now. The other one is a more advanced topic. I'll show you it, but you really need to understand this Pokemon example. Now, don't be fooled. I mean, Pokemon, it seems like it's a fun topic, it's a silly topic, it's not important. But I think as we were talking about it yesterday, Dylan said, well, this code is just like you'd write if you were writing for an Arduino. Yeah, this code is just the sort of stuff you'd write if you're poking at device registers, reading sensors, turning switches on a low-level embedded device. So this is a classic use of bit operations, and many of you will go on to do that sort of coding. So this sort of coding, even though it's in the silly context of a Pokemon, is crucial to understand. So this example, I'm saying, if you haven't understood it yet, do so. Now, I need to represent a Pokemon. I need to store 16 possibilities about a Pokemon. A Pokemon could have any subset of these 16 types. I guess it conceivably could be all 16 types. Perhaps it could be, I don't know if you have an empty Pokemon that has none of the 16 types, but it has some of these types. So it might be Dark and Ghost, it might be Ghost, Dragon and Bug, it might be Psychic, Ice and Bug. The classic way to do this, and perhaps the sensible way to do it in most contexts, would be just say, well, I'll have an array of our Pokemon. I'll have a 16 element array. That would probably be a better hash to find, and each array element will say whether that Pokemon has that type or not. So if I use that approach, and I'm not saying there's anything wrong with it, it's a sensible thing to do. There are 2 things. well, now there's really one thing. It's the amount of memory involved. That would use 64 bytes to represent a Pokemon. So many situations we don't care. That's fine. But there are circumstances there are two sorts of circumstances where we do care. One is if we have a huge number of the objects. For example, we had billions of them. Then the memory cost starts to become important. And we do see that in certain contexts. For example, to do with perhaps pixels in graphical displays or videos or things like this. Or if you're building vast models of things, you then suddenly have to worry about compactness in your storage representation. The other place this matters is if you get to tiny processors with tiny amounts of RAM, and we're talking Arduinos or similar tiny little embedded devices, little CPUs, where we're very resource limited, and then it also may matter. So here's my alternative. Instead of using an array, I'm going to use individual bits, and if a Pokemon has the type, that bit will be 1, and if it doesn't have the type, that bit will be 0. That means I only need 16 bits or 2 bytes. So this is 2 bytes versus 62, a storage saving of 32 times. So how do I represent this? Well, I can do it with hash defines, which have a 1 set for that type. Now remember, C doesn't have a binary notation, but hexadecimal works really nicely here. You can read that and see each of those values has just a single bit set, and they're disjoint, and we can see each of one of these has one of the 16 bits set. That's very nice. Let's run the run the program. I'll run the program and then explain. Hopefully I've got it here compiled. Pokemon, and I'll run. All right. So here we're seeing the bit patterns. I'll actually make that a little bit larger while I'm talking to you. Well, here we can see the 3 bit patterns. This is the bit for bug type, this is the bit for poison type, this is the bit for fairy type, printed out here. I want a Pokemon that's got all of those 3 types, so I can achieve that by ORing the 3 values together. That ORs bug type, which is 400, with poison type, which is 10 hexadecimal, and fairy type, which is 8000 hexadecimal. No, hexadecimal base 16. This gives me a type that's just got those 1 bit set. You can see if I do that ORing, I can reverse it. I can look at that and see what produced it, because none of these have the same values, have the same bit set. That gives me a possibility then. It gives me simple code to test things. If I want to know if a Pokemon is poisonous, I can just AND it with poison type. I can AND it with 0010, and if that produces a non-zero value, the Pokemon is poisonous. Similarly for ghost type, and this code demonstrates this. It prints out poisonous, doesn't print out scary, so that works. What else can I do here? This also, you have to understand this. This is all crucial sort of code. Suppose I want to add a type to a Pokemon. I decided my Pokemon is acquired ghost type. I can do that with an OR. So you remember OR equals, you've seen plus equals, OR equals is just like plus equals. So that's our Pokemon equals our Pokemon or ghost type. So that adds a bit, if you like, to that. Removing a bit is more interesting. So how do I remove a bit? If I say not poison type, I get a value that's got zeros everywhere poison type has ones, and ones everywhere else. And if I then AND it, that will give me our Pokemon with all the same bits except the bit for poison type. It will be removed. You're saying, Andrew, I don't understand that. Well, what I'd encourage you to do, I've said this, but let me show you seeing is believing. I want to understand this. Get these programs and run them and change them. So if I want to know what poison type looks like, I want to know what not poison type looks like. Assuming I can type, I can print this stuff out. I could do it with a print. Print bits gives me binary. If you're comfortable with hexadecimal, you could just print it hexadecimal. Let's even put a string in here to say I'm debugging. Alright. Let's this time for sure. My life. Alright, there we go. Spell printf properly. And we'll run this and we'll see the mask. We'll see the pattern here. We would if we had new lines there. Nothing is as easy as it thinks. You know, you're thinking, I can't be bothered with this. It's too much work to put a. This is not time wasted. Often to get a useful information, it'll take a bit of fiddling. Often a few minutes fiddling will save you, and getting the right information will save you a lot of time in the long run. Alright. So here's my debugging output. This is the sort of stuff I want you doing. I've printed out the bits. That's the poison type. That's not poison type. And then if we AND our value with that, that has the advantage, that has the effect of chopping out that bit. So this bit was set here, we AND it with this value here, the end result is we get a value without the bit set. Unless my friends Dylan, Zach or Jashank have something to add, or there's a question from the chat, I'm going to leave you with an exhortation to understand this code, add debugging, make sure you understand this program. It's a nice use of bit operations, and it's the sort of place you might have to use bit operations in future. How are we doing in the chat?
Not much really happening in the chat.
That's the voice of Zach, by the way. For those
Hello.
So Zach and Dylan and Jashank have joined us. So Jashank his laptop is falling apart and he's looking very worried. It's losing 500 milliseconds a second or something, or it is. We all have our troubles. Alright. Having shown you that, which is absolutely crucial, you figure this out, you make sure you understand everything. We'll go to a more advanced use, and if you don't freak out about this one's more complicated. This is a more general. So what was this doing? This was that previous example was representing a set. So this is a more general program to represent a set. I'm first just going to run the program. So ignore the code on the left for the moment. Let's see what the program does. It lets us store sets of numbers between 0 and 63. Yeah, why 63? Because I think 64 might be 2 to the 6th, I think. Alright. Let's try this out. So let's enter two sets, 5, 6, 7, 8, 9, and 45, 46, and 47 with a negative number. And we'll enter 6, 7, 46, 47, 48, 49, and a negative number. Right, so we've got a little program that represents sets of numbers. Oh, and I said it's because 64 is 2 to the 6. It's because 64 is the size of the type we're using to represent it right here. What are you thinking, Andrew? So we're using a 64-bit value to hold a set, so we can represent whether the numbers between 0 and 63 are present. The wrapper code lets me enter two sets, A and B, and then it does some setup. It prints out what the sets are and then does some set operations for us. So I've represented a set of the small integers 0 to 63 like that, and then I've done some set operations on it. There's code here to print the set, to read the set in, to do intersection, union, and add. Oh, look at intersection and union. They are so simple. Adding a value to the set, also interesting. Checking if something is a set member, also interesting. All right, so if you're very comfortable with, for example, the last example I did, go away. No, don't go away. Later, read this code and understand all of this. So this is a nice bit operations. For the circumstances, there's really two circumstances here that would make this interesting. One is I'm worried about memory. I don't want to use an array to represent the set. I'm worried about needing a limited amount of memory. And two, I only have a few possible set. I want to represent my universal set is small in number, so it's less than 64 in number, and I'm worried about memory. But it's a lovely use given those not so common constraints, but certainly possible constraints. This is a lovely use of bit operations to do this. But this is if you're struggling with bit operations, don't bother about this example. The last one, Pokemon, figure it out. This one, maybe come back to this in a few weeks' time and see if you can understand it then. That's it. All right. Let me take a breath, and if there are no questions in the chat about bit operations, we're going to move to another topic, which is going to be floating point numbers. Oh, there was a question there. Someone was saying, isn't this a global variable? Full points for being worried about global variables. We'll talk more. There'll be so in COMP1521, your first program, we try to keep global variables just a secret, and if you do discover it, we say that bad. Well, as we go through this course, we'll be able to tell you more about what some of the issues are with global variables, particularly when we get to threads and concurrency at the end. We'll show you some of the issues with global variables. So you're right to be worried that this might be a global variable. This isn't a variable at all. This is a type definition. This is saying everywhere I say in my program set, I mean uint 64_t. Now, some would tell me that this is actually poor programming style. It's pretty important to be able to recognize new types. When we're all used to the standard types, int, double, char, it's pretty important when you're reading a C program to see something and know it's a type. So to see set there as a type. So people like to have conventions for flagging things as types. One is to put an _t on them. There are other options. Some people capitalize the first letter. There's not a single universal convention for that. So you could argue I could have made that type clearer. The second thing is that good programming to use a type called set? Set, such a common English word, it maybe doesn't read very well. Maybe I should have called it small set or something like that, or small set type. But anyway, I guess it's an argument. The person in the chat saying, "Oh, that was a bit confused by that." That's probably an argument. You haven't made it clear enough what I'm doing there, isn't it? All right. I thought the floating point slides were up. I tried to put them up before the lecture. My apologies to Chen. I tried to have the floating point slides up before the lectures, but we'll get them up soon. That's so. As hard as we try, there's maybe reload your screen then, Chen. Reload your web browser. But I would say we try as hard as we try. There's always things like that we forget. We don't get something up, and a link's broken, and Autotest doesn't quite do what it's supposed to do. Just let us know in the course forum, and someone will be right with you and hopefully be able to address it. Many things go wrong, but we've got this huge team of smart people, tutors, to fix things. So hopefully we can fix all the problems for you. All right. Okay. Let's move on. Yeah, when I say fix all the problems, we can't fix Felix's laptop charger, for example. Sorry. We can fix your problems about COMP1521. But we all feel for you, Felix. All right. Floating point numbers. Oh, wait a minute. Is that the slide I want? No, I want to... Have I got confused? That's the one I wanted. Right, but I think I want to go to slides first. Where are we at with slides? These are the... There we go. All right. Floating point numbers, fractional numbers. All right, you've had a long exposure to them since primary school, probably. You've seen fractional numbers written in a floating point form where you write out 3.82. And there's a decimal point sitting in there to say it's fractional. So, C has types for these. Yeah, I guess you've seen them. You've seen one of them. There's a standard type, which you need a good reason not to use, I would say. So if you need to store a fractional number in your C program, the type double is your friend. When wouldn't you use double? I can think of a couple of circumstances. One circumstance you wouldn't use double is if you had to store billions of them and you were worried, had memory limits. You might not then use double. Another one is money. I don't know a lot about financial computing, but I think banks typically don't use floating point types to store money. They do their calculations to a certain fraction of a cent or whatever, so that it causes them problems if they use double for money. Where else? It is possible to have more precision in your calculation. Don't panic, we're going to talk about this at great length. You might want that in some circumstances, but then you have to really know what you're doing. If you don't know what you're doing, just use the type double for your floating point numbers. It's a little confusing. Yeah, there's a type called float. Doesn't that sound like the natural one? No, double. Basically, your friends are int for whole numbers and double for fractional numbers. But unless you've got a reason otherwise. Now in this course we've got lots of times we've got reasons to use something other than int. You saw uint 64t, for example, just in the previous example. We want a certain number of bits. So there we've got a reason. We'll talk a little about the possible reasons for double. All right. Oh, this would be your programming reminder. If I say 3 times 7 in C, what is the answer? The answer is, 3 divided by 7. 3/7 in C. It's int divided by int. And in C, they made the choice that an int divided by an int is an int. It's a choice. It's a design choice. It doesn't have to be that way. Languages have made other choices. Other languages have made other choices. Other languages have even changed their choices. Was it Python 2 to Python 3 I'm thinking of? Where what happens when you divide an int by an int changed? I'm struggling to remember there.
Yes, it did. They had to introduce a new operator.
And that's good afternoon to Dylan, who you're listening to there. Whose memory for what happened. I was around for the change from Python 2 to Python 3, of course, but my memory's not so good. So Python has changed what it does with the division operator. So yeah, it's a good example of being a choice. So an int divided by an int. The other question is, what int do you get in C? If I do 6/7 in C, what int do you get? And the answer, you might think, well, it rounds, of course. It rounds, and you get 1. No, it truncates, and you get 0. The story's a little more complicated with what happens with negative numbers, but it truncates. So you want to be very careful of division with integers. Now, don't worry, things get a lot better defined. Well, not better defined. Yeah, they're more defined. So C defines more, and everything works much better once we go to these floating point types. Oh, let's look at some code. So there's the three floating point types, and I've included this weird include file float.h there that gives me the bounds of the types. And I'm also printing out the size of the types, and I've got that compile ready to go, so let me run this program. You're saying, is there nothing in this course that can't be explained by running a C program? Well, when we get to assembler and MIPS, sadly, we have to run other programs. But yes, that's really how this course works. We write programs that explain things. There we go. So there's some useful information about three types. A float on this platform is using 4 bytes. A double is using 8 bytes. Now, I went on and on again about, yeah, you can't really count on an int being 4 bytes, and these things can vary. There's almost no variation in float and double. It's a rare platform where they're other than 4 bytes or 8 bytes. But what you can't count on is having them at all. It's possible you'll finish up on a tiny little processor that doesn't have floating point arithmetic at all. So you can't count on floating point arithmetic, but if you've got them, they'll probably provide floats that are 4 bytes and doubles that are 8 bytes. We'll talk about why shortly, but there's a nice universality there. Long double is a larger type, and look at the values it can represent. With a long double, you can represent 10 to the 4,932. I'm not sure why you would need that, but you can. Now, long double is not so universal. Well, I think it'll always be 16 bytes probably, but what's done inside the 16 bytes is less universal yet. I'm not even sure you can count on the 16 bytes, honestly. So long double, it less dependent on, but float and double pretty much the same everywhere. That's the closest value to 0 you can represent with a float. Seems pretty small, but if you're a physicist doing calculations in seconds about the evolution of the Big Bang, that's actually, they certainly get, I don't know if they talk about what's happening at 10 to the minus 35 seconds after the Big Bang and so on. So yeah, a float might not be good enough for you if you're a physicist studying that sort of thing. Most real world things, though, those bounds encompass us nicely, unlike the bounds of an integer, for example, where we can easily hit problems. Alright, they're the ranges. Let's go to my next, what's my next? Oh, alright, so here's printing out a value. I've done int, so 4 is an int divided by 7.0. Now, what type is 7.0? Excellent question. So you're thinking, well, that's a whole number, isn't it? It says, so that's an int. No. Once you stuck in a decimal point in there, C says, oh, that's a double. So 4 divided by 7 is int divided by int and gives you 0. 4 divided by 7.0 is int divided by double and does a very different thing. We can see what, well, rather than just waffle on here, let's just run my program. Now, it's occurring to me that, yeah, perhaps you don't need me at all. You could just write programs like this, discover everything for yourself, and it'll all be good. That's fine with me. We'll have assignments, exams, you do those, we're happy. But most of us need to sort of take a journey, a guided journey through this stuff. So, alright. All right. So what have I done? I've used %lf to print out D. Why is it LF? Why isn't it %D? D was already taken for decimal. So when you want to print an int out in decimal, D was already taken. So they had to go for LF, which is short for long float. You can do it in scientific notation, and that's quite nice to see, because we'll actually be using something like scientific notation shortly. Just a reminder for you what this means. Scientific. I'm hoping. You never know, do you? So I'm hoping that scientific notation is something everyone has seen. But if I say 5.7 e to the minus, e minus 3, that means 5.7 times 10 to the minus 3. And as the wording would suggest, this sort of notation is fantastic for doing science. It's a nice way of writing numbers. So, yeah, what do you think about it? You're that physicist working on the what happened in the Big Bang. If you have to write out all these values that are, start off with 35 zeros and 0.00000 35 zeros as that fraction of a second, as the universe is forming, that gets a bit tedious. You'd much prefer to write it out as 2.3 times 10 to the minus 35. Scientific notation. We all think it's a good idea. %LE there. G, saying to printf, you take your call, printf. You can use F or you can use G. Sorry, E, whichever you think works out best for me. You're saying there must be a rule. I'm sure there is a rule. You can go and research that rule, but G is not a bad format to use. Now, by default, this is printed out 6 decimal places. That's just a completely arbitrary choice made somewhere in printf. There's no reason for 6. Is there a reason for 6? Well, I guess, no, thinking about it, there probably is a reason for 6. It probably lies in the scientific background of the people who originally designed printf and all of these things. They're doing measurements. And honestly, you're measuring anything. You're working hard to get 3 decimal places. 4 is fantastic. 5, you're publishing papers. 6 is revolutionary often for a lot of things. So they decided we'll print things out to 6 decimal places. Now, it doesn't. If you're not doing physical calculations, that sort of reasoning doesn't apply at all. But that's probably where the 6 comes from. So if you want more decimal places, you can get 9 by saying .9 here, or you can also specify a field width. That's all that fun with printf. I think I saw a question in the chat, which was, you can omit the L there, can't you, Andrew? And the answer is, for lesions related to type promotion, yes, you can. I wouldn't recommend doing it because you can't for scanf. So for sort of weird reasons related to type, well, not weird reasons, for complicated reasons related to type promotion, you can tell printf you're passing it a float and it all works. But don't do that. Put the L in there, and then your printfs and your scanfs match up. Alright, that's printing out floating point values. That's assigning one. It all looks lovely. What now then? Oh. Here's something you perhaps didn't know. On my right is a program, and this is a thing of joy, by the way. This is amazing. Even the first line is amazing. If it's an integer, dividing by 0 in C is undefined. So you divide by 0 in C, what happens is undefined. And that's a major hassle. If it's a floating point number, it's handled in a logical and reliable way. This is amazing. I've got it already. Let me run this program. So if I divide by 0 and then print out what it is, so I said x is 1 divided by 0, what do I get? It prints out inf, which is short for infinity. Those of you who have done more maths than me can tell me whether it really is infinity or not, but the point here is rather is we get a guaranteed logical computation which we can work with and does sensible things. We can also get negative infinity. We can try subtracting 1 from infinity, and my maths lecturers were pretty clear about this. You subtract 1 from infinity, it's still infinity. Also, if you add 1 to infinity, it's still infinity. And doubles in C. C's floating point arithmetic does exactly what you'd expect from sitting in your year 1 maths lectures. But there's more. I can say arctan of infinity, 2 times arctan of infinity, and it prints out pi, which honestly I don't remember is the correct answer, but I'm hoping it is. Your study of these things is somewhat more recent than mine. I can also ask the question, is 42 less than infinity? And again, we get the answer of true, 1. And we can even do a comparison. We say, is x infinity? And get 1. So we can do all these logical operations with infinity. It's great. It really is. Yes, it's a double. This value is a double. By the way, 42 here is an int, but everything else, oh, that's an int, there it's 2. But if I put an int in any operation with a double, it'll get turned into a double. So I could make all of those doubles if I wanted, and it would have no effect. But why would I do that when you can do this? You can get this program, compile it. I can't say this too much. Get programs like this, experiment with them, understand them. Yeah, there's lots of studies in education and things like that that shows that learning done that way sticks better. All right, that's infinity. That's a nice thing we get. What else do we get? Oh, all right. This one's a bit weirder. It's a nice acronym. It's sort of comforting, isn't it? If you've heard people call their grandmother Nan, it seems comforting. Generally, it's not so much. Normally, you're upset by the time you get to if you see nans coming out of your calculation. But nans are a wonderful thing. All right, so nan in this, what have I done here? I've divided 0 by 0. Again, you'll have to go chat to your maths lecturer to really get into the meaning of that, the semantics of that. But it produces something that we don't want propagating through our calculation. So it produces a bad result that we don't want propagating through our calculations. There are some things we could do here. We could stop the program here, but that's probably not what we want. It is possible to configure your floating point, I think, to do that, but rather what we don't want is this value ever being used for anything. We've done something that's not mathematically sensible. We don't want this value used for anything else. So we have this concept of we've got a result that is not a valid number, or nan, not a number. So certain floating point operations produce this nan value, and then this just this nan value will just keep propagating through our computations, and we won't fool ourselves. We won't. The error that occurred here won't get hidden. It's a wonderful thing. Trust me, it's a wonderful thing. So if you print out a floating point number like that, it could write out nan meaning not a number. Now if you apply computations to that, you'll still get not a number. Multiply it by something, add something to it, do anything with not a number, you still get a not a number. Here's a good one. This is my favorite actually. This is really good. You're saying x equals x. If x is an int, that's always true. So if x is an int, you say x equals x, the compiler will pre-compute that and say that's always true, and it'll pre-compute that and optimize your program. if x is a double, we don't know for sure that that operation will be true, because not a number is not equal to not a number, because then it's not a single valid concept. We've done a computation and got not a number. We do another computation and get not a number. Then they're not necessarily the same value. So the sensible thing is for this to be false. How do you know then if you've got a not a number value? You have to go to a built-in function to do that. There's a built-in thing in the math library to say, is my value not a number? Now again, this consistent logical handling of what happens when you do something that's not sensible, this is amazing. This makes floating point arithmetic so much better, so much safer. This and the last one, inf and nan, they save lives. They save many lives from they save and billions of dollars in by stopping people making erroneous mistakes in their calculations. And leading up and hiding it from them. These means the mistakes in your calculations are shown to you normally. I'm not a guarantee that you can't still kill people with floating point calculations or lose millions or billions of dollars by doing stupid things with floating point calculations, but they at least cover a couple of the common cases. What else have I got? Yeah, we're going to have to switch soon to looking at representations to understand this. Do we want to see that? Yeah, I'll run this program, and then we're going to have to go and look at how floating point numbers are represented and think about it. So I've got this program here, double in precision, and it doesn't quite do what we'd expect. Let me run it. So I've got two values here. I've got a is 0.1, and I've said b is 1 minus a plus a plus a plus a plus a plus a. And there's 10 a's there, so that all should finish up as b is being 0. Then I've said if b is not equal to 0, print out that. And what do you know, it prints it out. And discover why the %g format is my friend here. Actually, let me show you the value of the %g format and how it's giving you a bit of help there. If I just said %f here, it would have told me b was 0. Well, sort of. I've got to compile it. Bear with me. Double in precision. Recompile. That will just print out zeros for me. Let me show you. Am I telling the truth? I am telling the truth. Actually, I might flip my head to the left now. Oops. There we go. So we did this calculation. Yeah, you've probably spotted the problem. B is a tiny value. But if I just use %f or %lf to print out b, it'll just say 0.000. It'll just say 6 digits of 0, but it's not exactly 0. And %g is my friend, as would %e. So if I say %le, I'll get it printed out more usefully. And you'll remember, G just makes a choice between printing it out in scientific notation or just printing it out with a regular decimal point, and it decides which is best. And because it's a very small value, it'll decide scientific notation is the nice way to print it here. But this leaves the question, why did B finish up as a tiny value, 1 times 10 to the minus 16, when it should be 0. I mean, mathematically it should be 0. 10 times 0.1 is 1, 1 minus 1 is 0. Why? Why did we get this very slightly wrong answer? I'm going to cover that at length, but first I'm going to say this again and again. But another of my life tips, another way to have a happier life, is never ever put equals equals or double equals next to a floating point number. So don't have double value equals equals or not equals. That is dangerous. It's all, if you've got a double value, comparing for equality is something that's generally best avoided. If you really know what you're doing, and I guess if you go through this course and understand everything we're trying to teach you, you will know what you're doing. There are cases when you can do it, but honestly, if you want to be safe, just don't. You always should use less than, greater than, and their friends with floating point values, with double, with float, with long double. Because, well, and this program is that in miniature. Yeah, someone's asking, should I use LG? Well, I mean, output depends what output you're trying to achieve, but generally for debugging, yeah, LG is pretty good for debugging. %LG is pretty good for debugging. If it's a lab exercise or something like that, we'll often give you a format because you've got to match the auto test, and we'll say you use % this or % that or whatever. But LG is nice for debugging, yeah. All right, now let's go to my lecture slides then. I'm going to take a break soon. Don't panic. I need to stop talking soon. I've been talking for so long. What's my problem? My problem, and it's again, I think it's a first year maths topic, is the number of real numbers. I really should find out what they're teaching in first year maths now, and rather relying what I was taught on so long ago. But it's the number of real numbers that is our issue. How many real numbers are there? How many possible floating point numbers are there? And you're saying, I think it's infinite. Yeah, that's what they told me as well. But it gets worse. How many floating point numbers are there between 0 and 1? Yeah, there's an infinite number of floating point numbers between 0 and 1. What about between 0 and 0.1? Still infinite. 0 and 0.001? Still infinite. Any interval, infinite number of real numbers in the interval. It's a bit of a problem. Why is it a problem? It's a problem. Well, I'll show you why. It doesn't have to be a problem, at least if you stick to reals, I guess. Was it reals? Let me run this. The problem is here. If you have a fixed number of bits for your floating point representation, if you're happy to use any number of bits to represent your floating point numbers and let it grow arbitrarily, then you can probably do something useful with the reals. You get into issues, I think, with transcendentals and things like that, maybe, I don't know. But that's not what we want to do, because that gets really slow, and we want to do fast computations. If you want to do fast computations implemented in silicon, we've got to go to types with fixed numbers of bits in their representation. So we're saying I'm going to use 8 bytes or 64 bits. So I've got 64 bits. That's a lot of patterns, actually. That's 2 to the 64 patterns. I can convert that to a power of 10, I think. So I said 2 to the 10 is approximately equal to 10 to the 3. So that's 2 to the 64 is about 10 to the 18. Have I got that? maybe 10 to the 20 patterns. We'll say roughly 10 to the 20 patterns. Seems like a lot of patterns. We've got 10 to the 24, 10 to the 20 bit patterns, 2 to the 64, sorry, approximately 10 to the 20 bit patterns, 2 to the 64 bit patterns. So a lot of bit patterns. The problem is infinite number of reals. There's no way around it. We've got finite number of bit patterns, we've got a hell of a lot. There's an infinite number of reals. Almost all the real values will have no exact representation in our finite representation. There's no way out of that. We can't represent the infinite number of reals exactly. Even if we've got two things represented exactly, if we do a calculation, the result may not be something which we can represent exactly. Now, what can we do about this? We can have representation spread through the real numbers, and we can just use the closest value. And as long as that's pretty close, maybe that's all we need for our purposes. And that's what C does, and that's what the underlying floating point representation does. But it introduces an error into our calculation. Often this doesn't matter. There's a lot we can do without it ever mattering. Sometimes it can be disastrous. But it's this notion of approximation. We're all representing floating point numbers approximately. So this is my problem in this program. It's the 0.1. Turns out there's no bit pattern for a double that represents 0.1. So the bit patterns we've chosen for floating point numbers, out of all the 262 to the 64 possible bit patterns, 10 to the 20 possible bit patterns, none of them is exactly 0.1. There's one that's very, very close, only 10 to the minus 16 away or something of that order, but there's none that's exactly 0.1. Alright, and that's our issue. Now, we're going to get much more into the details. We're going to take a break shortly. Let me see if we're at a good point to take a break. I think we're actually, might be at a good point to take a break, because we're going to go into the exact... Yeah, this is actually a good time to take a break, unless Zach, Dylan or Jashank have something they want to interrupt with. I'd like to take, I think, a 5-minute-ish break and start at 5 past the hour. Give everyone a chance to get something to eat, stretch, and so on. I'm hearing silence from everyone else. So, alright, let's take a break and... yeah, everyone take a break, bit of yoga, something like that. Maybe not some, yeah, you can do some yoga, stretch your, get up, blink and so on. We'll be back at 5 past the hour. Enjoy the lovely frog while we're out. All right, welcome back, everyone. Yes, we are going through. Excellent. Okay. So let's come back to our fundamental problem. We want to use a certain number of bits for for a double, 64 bits, fixed number of bit patterns, infinite number of reals. So what do? As I said, you could make the choice. No, I'm just going to use an arbitrary number of bits. I'm going to use 20 bytes, 30 bytes, 100 bytes for a single floating point number, and that's fine. There are circumstances you can do that, but it's going to be so much slower. I'm talking thousands, tens of thousands, or hundreds of thousands of times slower, perhaps. So you can avoid this, but at a huge cost. For most of the things we want to do, we get by using fixed length representation, which we can implement entirely in silicon, and it can go fast. So fast. Although actually one thing to remember is it's fast comparatively compared to doing sort of general computations in our programs. It's not fast compared to integer arithmetic. Floating point arithmetic will always be slower in the silicon, if that matters to you. And we can get little chips, little CPUs, where the CPU is too small to have floating point. They didn't have enough transistors to put the floating point on board. And your washing machine might, for example, the CPU in your washing machine might not have floating point.
Indeed,
right.
The first PCs didn't even do floating point really by default.
Please don't remind me.
Was
It was a horrible world. These days, it's tiny embedded. Your microwave, your toaster, things like it. Maybe your routers, I think, often have floating point. Typically have floating point. All right. So we get by. We represent 2 to the 64 real numbers exactly. The rest we approximate. We use the closest value that we can represent exactly. But the problem is, if we get two numbers we represent exactly, do an arithmetic operation, plus, minus, times, we'll finish up with a number which we can't represent exactly and we have to approximate. And it can be disastrous. So we have to understand this, and we have to understand the very bits used to represent a floating point number. And as I said, that there's some fantastic news. Almost all floating point number calculation is done in the same way. I've said C doesn't quite guarantee this, but there are basically 3 cases. You're on a tiny processor, no doubles, no floating point calculation. You're on most processors, it works exactly the same way. Doesn't matter if you're on a Mac or an Intel PC, you're running Linux, you're running Windows, all the same. Any sort of general purpose computer, all the same. There are weird special purpose computers that do signal processing and things like that. You want to do radio astronomy and things like that. The processors you use do floating point arithmetic in weird ways, and they may be different, but very unusual. So yeah, it's a much better world. So there's so much software. We go from, say, a Mac to a CSE box, and things have changed. Floating point numbers? No, they don't. My floating point number program works at CSE. It'll work on a Mac. It's amazing. All right, first, let me describe something that we could do and sort of works, but isn't used much. The place it actually is used, I mentioned banks and don't use floating point representation to store money. What they use is effectively fixed point representation. So what we could do is assume, when we're going to represent numbers, we've got 2 parts. We've got the part in front of the decimal point and the part behind the decimal point. And say, for example, if we had one to do with 32 bits, we could say 16 bits are for the part in front of the decimal bit point, 16 bits are for the fraction. This works really well in one way. So it's easy to implement, works sensibly. It's easy, easy to implement in silicon. It's actually what you do if you don't have floating point. So if your washing machine needs to implement things that sort of look like floating point numbers, the level of water in the tub, it'll do something like this. It'll do something like fixed point representation. How does it do it? Well, this looks very much like scaling the value by 2 to the 16th. So if I can only represent integers and I want to represent fractional values, I just multiply them by enough so they become integers and then do it that way. So if my washing machine, it says, oh, I have to deal with fractions of litres. Well, maybe you don't. Maybe you only have to represent tenths of litres or hundredths of litres. So take your value, multiply it by 100, and now you've got an integer. Away you go. Fixed point arithmetic is just a general way of doing that. It's not something we're going to cover further in this course. You want to know more? Wikipedia is so much your friend. I would caution you, not so much at this time of year, but as the term goes on, diving into Wikipedia, endlessly exploring Wikipedia, may not be productive in terms of marks. In terms of learning, yes, but if you've got a maths exam in 2 days' time, no. But it can explain, if you want to know more, Wikipedia about fixed point representations. All right. What's better is floating point representation. Let's keep going. So, first, I've said floating point works the same on your laptop as it does at CSE. That's because there is a standard dating to, I think, to 1985. It's a standard that's been around for a very long time. It's a there's a wonderful, a person who's achieved a lot, a Canadian computer scientist called William Kahan, who's still around, but he must be about almost 90. He was at Berkeley, University of California at Berkeley for many years, and in the sort of early 80s, as he set out to make floating point arithmetic, to standardize it, get it done right all over the world, and get it done in a one way all over the world. And him and his colleagues, people he worked with, did amazingly well. And the fruits of their labour is a standard that goes by the lovely name of IEEE 754. What does it set out? It sets out a few things, but basically it says you've got 64 bits for a floating point number. This is how you're going to represent floating point numbers with those 64 bits. So it says what those bits represent, what they mean, and they're the same on your laptop, a CSE server, on most general purpose machines. On most of these, if you look at a bit pattern, that's the same. Sorry, on these, if you have a bit pattern, it has the meaning IEEE 754 meaning on all of those. So that's wonderful. That means the silicon in the chips in them implements the same meaning. All right, there's a few of these standards. We're actually going to, for convenience, we're actually going to pull apart the 32-bit representations. So the 32-bit representations, just because it's less bits, the 32-bit representation is very similar to the 64 bits. There's just more bits used for everything in the 64-bit. So if you understand the 32, you understand the 64. So there is actually now a 16 one that's fully defined, which we could do, but anyway. It's not available in a normal C program at CSE. So 32 is. So it's nice to work with the 32 one. So 32. That's the standard for floats. There is a 128-bit standard, but it's not as uniform yet as you'd like because of the silicon. I'm not hugely up to date on this, but I understand a lot of silicon hasn't got to providing that, so a lot of processors don't provide that yet. But binary 64 is everywhere. Now, how does it work? What's the insight? I guess the insight is we've seen how physicists switch to writing things as 2.3 times 10 to the minus 35. So we've seen that. And that works much better than writing 35 zeros and then a 2, 3. So scientific notation's convenient just for us writing stuff. A similar sort of approach works well for representing reals. So it works well for coming up with good bit patterns, good ways of doing bit patterns. Now 10, we don't want power of 10, of course. So real representations are based around powers of 2. So everything's binary, but it does follow this form where we've got an exponent and what often gets called the fraction or the mantissa. So we do fraction times 2 to the exponent. Gee, my writing's bad. So everything is, we'll have a fraction times 2 to the exponent. Now, sadly, that's not quite the entire, well, there's a bit of a complication here. The fractions are done in a slightly weird way, the exponents are done in a slightly weird way, but we can figure that out. But this is the key realization with how we represent a double inside a computer, that we go to this form of, we're going to have some bits for the exponent and some bits for the fraction, and what that means is fraction times 2 to the exponent. Alright. Now, there is, we'll come back to this. There's some, the bias and the normalizing, they're the complications I talked about. We'll come back to those. Oh, here we. Don't have to come back to them because I've got a nice slide explaining them. Alright, so there is a floating point binary number. What binary number is it? It's 10.6875 apparently. Is that right? 8 plus 2 plus a half plus an eighth plus a 16th. Yep, that seems about right. There are a few ways we could write that in pseudoscientific notation. We could write it as 1010.1011 times 2 to the 0. We could write it as 10.101011 times 2 to the 2, and so on. Now, it's not nice to have multiple representations. So it would be complicated if there were several bit patterns possibly representing the same number. So remember, we're doing everything as fraction times 2 to the exponent, but we don't want multiple ways of doing it. And just in that form, by changing the exponent and changing the fraction, you can get two values that are exactly the same. So 1011 times 2 to the 0 and 10.10101 times 2 to the 2. So we need to have some rule to say we'll only ever finish up with one bit pattern. The rule is that the decimal point will be always immediately after the first digit. So we'll always have 1.0101011 times 2 to the whatever. In this case it's 2 to the 011 or 3. So we'll always insist that the decimal point is immediately after the first non-zero digit. So there's always a 1 here. This gives us a unique fraction and a unique exponent. There is an extra part of the story then. If this is always a 1, we don't need to store it. And we'll see that. I think it's time to get concrete. Let's use bit operations to pull apart the exact bit patterns that are used on CSC. We've got the bit operations that can pull apart a value. I've got a program to do this. Let's try it out. Let's see if that's illuminating rather than me explaining this. Alright. I have here ready to go a program. I'll show you the flavor of the program. Oh, it's complicated. It is a complicated program. Don't worry about that. But I'll show you the flavor, just to show you what's happening behind the scenes in terms of this. Now let's ignore all of that. Exactly. So it's using bit operations. Don't panic. This is complicated. But it's something we did before. It's extracting a bit range. It's converting a bit string. It's doing stuff. Printing bit range. It's using bit operations. Oh, and it's doing scary things. It does scary things. It gets a float, a 32-bit floating point number, turns it into an unsigned number. We might talk about that later. But it does weird things behind the screen, to get at the very bits of the floating point number. Let's look at the results of this then. I'll put that. That's a bit more calming. So let's try this out. I can give this any number and it'll tell me what bits are used for it. So let's give it 0 and ask it to show me what bits get used to store 0 as a float. Alright. Well, let's make some more room. And my program tries to explain why. And 0 is not super exciting, but it says, look, Andrew, the IEEE 754 standard for 32-bit floating point numbers said you want to represent a 0, you use these 32 bits, no others. So that's a 0. That's sort of nice, because there are reasons why having a 0 as 0 bits is nice in terms of initialization and things like this. But that's okay. It's telling me it's broken up into 3 parts. That's the sign, which is 0. That's the exponent, and that's the fraction. And if I break it all down, I get it's well, that probably doesn't matter for 0. Well, let's look at some other numbers. What did I want to try in there? Let's try one that 4.5. Yeah, another coincidence. I'm choosing something that should be pretty easy to represent. What happens to 4.5? So that's the bit pattern used to represent 4.5 as a float. That's the bit pattern used on my computer. That's the bit pattern used on your computer. That's the bit pattern, as I've said, used on pretty much every computer in the world, courtesy of the work of William Kahan and others in the 1980s, who set out this standard saying we do it this way. He did far more than that, by the way. He also came up with this really nice scheme of handling things like infinity, not a number. He wrote programs that would then go and sort of destruction test your floating point representation to make sure it worked well. So he handed out software to people around the world saying, you think your CPU works well? Here, run my program and make sure it produces the answers in all these cases. Testing, wonderful testing. All right. So now this looks a bit weird. All right, so the sign is 0. Let's figure this out. The sign is 0. That's the first bit of the representation. We can figure this out. Let's just check that. If we put in minus 4.5, it should be the same. It's got a 1 there. All right, so that's the first thing we've figured out. That's the easiest thing. The first bit is for sine. 0 for positive, 1 for negative. That's easy. Now the number is actually 1.001 times 2 to the 2 in binary. So the exponent is 10 or 2 and the fraction is 1.001. It's a bit hard to figure that out from, that's 10 base 2. It's a bit hard to figure out how that produces this exponent and this fraction though, isn't it? Which one will I do first? Let's do the fraction. If, when storing fractions, there 32 minus 9 is 20. 32 minus 9 is 23 bits for the fraction. If we stored that first digit of the fraction, that would be a wasted use of a bit because it's always 1. So we actually don't store the first one because we assume the numbers are normalized, so the decimal point is the second thing. So the numbers are scaled so that the digit to the left of the decimal point is a 1 and there's only one digit to the left of the decimal point. We don't store it, but there's effectively a 1 there and the fraction is 1.001. Alright, I shouldn't have erased that, so let me put it back. So it's 1.001 times, we'll do it in base 10, it's times 2 to the 2. How did that 2 get to be here? Alright, exponents are stored in a slightly weird way. We add 127 to the exponent and then store it there. So it's called the bias, doesn't mean a lot, you just add 127. So that will give us always a positive number to store for the exponent. So the exponent we want here is 2. You add 2 to 127 to 2 and you get 129. And if you do the calculation there, is that 129? Yes, that's 129 binary. So my program here is unraveling it. It looks at the exponent, says, oh, that's 129. IEEE 754 single precision says exponent bias of 127. So I subtract that, and that's the real exponent. Similarly, my program let's go through the steps of this being unraveled. I see this bit pattern. How do I unravel it? I look at the first 0. I say that's the first bit, that's a 0, it's a positive number. I then look at these bits. No. Not doing well today, Andrew. And then look at these bits, which are the fraction, and say the number is plus. So these bits tell me the fraction, and there's always a 1 there. So that's my fraction in binary. My exponent is sitting here. That value is 129. If I subtract 127 from it, I get 2. So that's my number. This is binary, and if you do the calculation there, that's 1.125 base 10 times 2 to the 2, which gives me what I want. If you've understood that just from going through that explanation, that's amazing. Most of us have a harder path to figuring out floating point numbers. So for most of us, we have to spend a lot of time looking through example after examples. I'm hoping this program I've given you will help you. There are also excellent online resources. We've linked a few of them into the class webpage, which do beautiful diagrams of various sorts. You can try looking at those as well, but I would encourage you to read the diagrams, see if that explains it better, then come back to the program and put examples in and make sure you understand then why 4.5 turns into this bit pattern, or this bit pattern turns into 4.5. Let me show you. I think my recollection is this program goes both ways. So my recollection is if I put a bit pattern in there, it will tell me what the value is. So this program, I'm impressed with my coding there. If you put in a floating point number, it turns it into a bit pattern. If you put in the bit pattern, it tells you what floating point number it is. That's quite nice. Alright, so I could actually muck with the bit representation. I can say, oh, if I change this bit to a 1, what do I get? And it should be minus 4.5. Or if I increase the exponent by I've increased the that will add 2 to the exponent, if I've got that right. I think that adds 2 to the exponent. That should give me 4.5 times 4 is 18. So that should give me negative 18. Oh, well, that's a fail. Negative 5.5. What did I do wrong there? I didn't manage to change the exponent because I edited the wrong bit. I changed the fraction. But if I was clever, I could do that. That will be negative 18 for sure. Nothing could. Oh, and it did. Look at that. So I can fiddle with this, and for any bit pattern, work out what number that is. If you want to be that person who can successfully work with computers with floating point numbers, there's no substitute for you getting your hands dirty, going right down to the bare metal and figuring out what bit patterns are used with what floating point numbers, what happens here, minus 5, what bit patterns it is. This gives you this deep, powerful understanding of what's happening in floating point computation, and then you will instinctively realize, hopefully, before doing bad things. Alright, there are a few more possibilities here we should check. What other possibilities should we check? Well, you're saying, let's check out infinity. Oh, actually, let's check that out. Is that the right number of zeros? I'm not sure. Oh, so it apparently is. Here's something for you. There's a negative 0. There are signed zeros in floating point representation. That's a bit of a worry, isn't it? Is that a bad thing? I don't actually have an opinion there. But note there, you can put the 1 bit there and do this. You can experiment with signed zeros and see what happens. Suppose we want to find out how positive infinity is represented. Tuck it into the program and it will show the bit pattern there for positive infinity. How do we recognize positive infinity? Sign of zeros, exponent of all ones, fraction of all zeros. That's how positive infinity gets represented. How does negative infinity get represented? Same, but a 1 there. How does not a number get represented? Spotting a pattern here, aren't I? An exponent of all ones is reserved. So if the exponent is all ones, it can't be a normal number. It's either infinity or not a number. There's a question about what's happening with these other bits, and you can research that if you want. So there are two special values for the exponent. The other one we've already seen, which is all zeros. So an exponent of all zeros is used for 0. An exponent of all ones is used for the special values. The other 254 possible exponent values are used for regular numbers. This lets us work out the range, by the way. The approximate largest and smallest floating point numbers are then 2 to the minus, we're subtracting 127, so it's 2 to the minus 126, I think, to 2 to the 126 is the approximate range of the float. You can do a more exact calculation, but we've got 254 possible exponents there. All right, that's nice. Let's just try some one or two other examples. I had some nice examples chosen up here. There's one. 0.1625. So if you're pulling apart this, we get first bit 0, so it's a positive number. Next 8 bits are giving me the exponent, so I have to calculate what that is. But if I work that out as that turns out to be 124 base 10. The bias is 127, so the exponent here is minus 3. So we've worked out an exponent of minus 3. So now we've got 0.01, and remember we've got 0.01 base 2, which is 1.25 base 10. So the final number is 1.25 times 2 to the minus 3. And is that correct? Looks correct to me. So get values like this, figure out the bit patterns, figure out the fractions, go through the calculations, make sure you understand all of this. You're saying, can I have lab exercises where I practice all of this? Yes, next week. Alright, that's quite nice, isn't it? What do I want to show you now? Maybe a very small number. Can I put in a very small number? Maybe 1 times 10 to the minus 50? Will that work? No, it's too small. Let's try it. There we go. So rather than type in 30 zeros, 0.00000001, I've told my program 1e minus 30. How does that turn into a floating point number? So that's 1 times 10 to the minus 30. The exponent's quite small. That's the exponent value, which is 27. So 27 minus 127 is negative 100. So our actual exponent is minus 100. So the number we get is 2 times minus 100. And we get a complicated calculations here to do that. You can figure that out, but apparently that's 1.26765 times that. That's not really. Alright, I think that's enough of that. I'm encouraging you to go away and put in things like this and understand them. I really want you, honestly, the world is a better place if people understand how floating point exactly works. Well, not everyone, yeah, okay, but everyone who's working with computers, they're doing calculations involving floating point, if they've really seen what's happening with the bits, the world is a better place. Now you're saying, Andrew, you're only telling me about float. Double is exactly the same. I can't remember. Double's exactly the same, except the exponent has more bits and the fraction has more bits. I don't remember what those either of those are. Zach or Dylan, can you remind me how many bits in the exponent for a double?
I have it up here. It is exponents 11 bits, fractions 52.
All right, so if you go to a double,
1 11 52. Yep.
if you go to a double, you get 3 more bits in the exponent, but you get 29 minus 32. You get almost 20 more bits in the. No, you get almost 30 more bits in the fraction. Which can save you from a lot of mistakes. All right, let's go. I've got some more programs to show you. Oh, excellent question from Brandon. Yeah, thank you, Brandon. That's a superb question. He's saying, do I always subtract minus 27? You do if it's IEEE 754 single precision. You do if it's, sorry, that 32 bits. So you do that always if it's a float. The exponent bias will be different for other formats. It's always the same all the way through the format, but for a double, that exponent bias is a different number. So that's different for a double. So that's the other. You get more bits with the 64-bit double format, and you get a different bias as a result. We're going to just keep working with the 32-bit format, just because less bits is less bits to write out. You understand the 32-bit format, you understand all the other formats. One day, if C has the 16-bit format, we'll do the 16-bit format in classes. All right. Oh. See, I'm asking you, and then I've got a slide here. So yeah, this is the difference between float and double. More bits, a few more bits in the exponent, lots more bits in the fraction. And this, why? Because it's not actually that much. Or floats already cover a big range of numbers. We don't actually, for most purposes, we don't need to represent numbers that are much absolutely bigger or infinitesimal. What we need is more precision in representing the numbers, so to reduce the likelihood of errors causing us problems. Doesn't eliminate it, certainly doesn't eliminate it, but it reduces the likelihood. But the bias here is 127, and I honestly can't remember what the bias is here. I could probably work it out, though. It would have to be 8 times 120. No, it would have to be 128 times by 2 to the 8 minus 1. You can work that out. Alright, so this is just showing you other examples. Alright, let's show you some more bad news then. Let's recap this. Here is the problem in this program. Doesn't look like, but that's the problem in this program. I've said to C, look, put 0.1 in A. C says, okay, I'm using IEEE 754 to represent this. What bit pattern for a double best represents 0.1? And sure enough, it goes and finds the best bit pattern, and it's almost exactly 0.1. It differs only from a tiny amount, absolutely tiny amount, but it differs. And then if I do this calculation, those differences affect the result, and the calculation is also out by a tiny amount. If I'd chosen a value, I deliberately chose 0.1 because there's no exact representation. If I'd chosen a value that had an exact representation, for example 0.125 has an exact representation, if I subtracted that 8 times, no problem. The problem is there's no bit pattern that exactly matches 0.1. You can try this out. What bit pattern do we get? Oh, this is for a 32 bits, but same difference. The bit pattern we get, if we print it out, it prints out as 0.1, but it's not exactly right. There's the pattern we're getting. We should actually print it. This program should print out what it really is, shouldn't it? That's a bit of a weakness. This is the number we can exactly represent, which is that in binary. Alright, let's see some more consequences of this. So this was a problem here. Well, 2 problems. One, I did this, then I did that. So I should have said, is B very close to 0? And then I wouldn't have had any problems. This is a weird one. Well, there I've said I'm doing a calculation and I'm doing things where we're getting we're magnifying the error. Effectively, the way we do the calculations magnifies the error that occurs. And this is a hard one. This is sort of the simplest taste of what is a hard problem when we're doing these sort of calculations. Then there are ways of rearranging your calculations to avoid these issues. So let's try it out and see how wrong the answer is. Oh no, I've compiled it already. It's called double catastrophe. The answer y is supposed to be very close to 0.5. So y is supposed to print out here as very close to 0.5. If you're a star at trigonometry, you can figure that out for yourself. But y is supposed to be very close to 0.5. The trouble is, we're doing this division here, and the values are very similar, and they're very small as well. The result produces a large relative error. How do you avoid this? There's not really an easy answer. You've got to be aware of this. If it's anything important, I would be reversing the calculations to see to check them. So I wouldn't take the output. You know, you've got a job designing the girders for the next harbour bridge, and calculations come out like this. You really want to be able to reverse them and see that they're correct, or calculate them in other ways. You need other reasons to believe that this answer is correct. You can get mathematicians or people who know what they're doing to look through these calculations and think about these things, look at those values and thinking, is that the best way? Can I rearrange that? If you've got more precision always helps and can get you out of this. I'll see if it's an interesting one. I don't know if going to long double would get me out of this. Let's see, does that get me out of this? Or does it still give me the same answer? Sometimes just throwing more bits at it is enough. Oh, all right. We want to put %LG there. Okay. Let's see if throwing more bits of this is enough. No. Didn't make any difference at all. I thought that would. Sometimes just going to more bits doesn't make any difference anyway. And I'm not sure how many bits of extra I'm getting with long double on this machine anyway. It might only be using... Alright. Let's not worry about that. I think if you went to 128 bits with this calculation, it probably would get the problem. But you can still construct further examples. This example's been particularly constructed because it's a simple thing that produces problems with 64-bit representations. But if you go to 128-bit representations, you can also construct catastrophic situations like this as well. And what do you do about them? You've got to be smarter in the end. Oh, I like this. I love this one. The comments are a bit of a spoiler here. All right, I can delete. Pretend you haven't. I should have deleted the comments. They're such a spoiler. All right. Go back in time. Pretend you didn't see those spoilers. Look at this code. You imagine we've got a big thing. It's something we're proud of. Is something we were proud of. Well, we're still proud of. A lot of work has been done around CSE improving the properties of programs. Proving, for example, your operating system is correct, secure, things like that. Proving properties of programs. We're very sad because there was a sort of joint organisation with the CSIRO that was funding all of this work, and it decided this year that this work was not important and moved to funding other things. But some of the people involved are still with us at CSE at least. So it's certainly a focus of this proving things are correct. It's enormously useful. Imagine, for example, you have to write code for a pacemaker. What a pacemaker does is really simple, really, really simple. Probably at the heart of something like a pacemaker, it's a tiny C program, page or two of code. But it is rather important that it keeps working. If you put a pacemaker in someone, you do want it to keep working, so you'd like to prove it's correct. There is also the question of updating the code. So it might only be not a very complicated program to put in a pacemaker, but if you discover got a bug, operating on someone to update their software couldn't be an issue. So it'd be nice to prove things are correct. So on screen is code, and you look at this and you think, well, this program must terminate. Termination is something we would like to prove. Oh, it's got the printf in it, but it never terminates. It's got a printf in there printing out D. Why is D never changing? Alright, this example is particularly chosen so that that's a very big number. It turns out that... Oh, actually, I can bring back the spoilers. Maybe that's the easiest way to do it. Alright, I'll bring back the spoilers. It turns out that if you add 1 to D, you get the same number. How can that be? This is one place that doubles are a bit dangerous. This value, D plus 1, can't be represented as a double. And it turns out the closest representation is the same one as for the number integer 1 less. So there are two integers, two very, very large integers, but two integers that have the same representation as a double. The end result is you add 1 to this value and you get the same value. It's a bit scary, isn't it? Well, A, it's scary, A, it's a lesson, but B, you don't understand why it is. Now, you're saying, oh, do I really have to worry about that a lot? The numbers have got to be pretty large before this happens, so it has to be anything that can be represented by a regular int, a regular 4-byte int. has an exact representation as a double as well. It's only when you get to this is the first double. Sorry, this is this one is the first double, the first integer that doesn't have an exact representation as a double. There we go. Alright, so that's another scary property. I think that might be my last little thing. Yeah. Alright. What do I want you to do to this? Nothing yet. So this week, for the lab exercises, I want you to get on top of bit operations. We've got so many things with bit operations in the lab exercises. There's so much to do. But I want you to practice all your bit operations, understand your bit operations, get on top of them. But before next week's Tute lab, then I want you to go back and understand the bits of a floating point number. So I want you to read up the description of how the bits are used, then I want you to run the program I've been running, copy it down from the class website. This program explain point representation and put in numbers like 11.25 and figure out why it turns into this bit pattern. So you should be able to work out how 11.25 becomes that bit pattern and the other way around. So try and do that before next week's Tute labs. This week, bit operations. Understand bit operation. Enjoy pulling apart binary coded, decimal, and these other formats. It's the challenge exercises. I think there's one that's just a challenge, and the other one is a sort of a super challenge. So if you've got time, take those on. But before next week, look at this representation of bits. And some of you, you're amazing. You've figured it all out from just listening to me lecture. Most of us have to work through it slowly in our head, go through example after example, get another resource, and then finally it'll click. That's how I get these bits, and I do this, and I do this, and it all makes sense. But work painfully through this arithmetic. Alright. At this point, unless Zach or Dylan, I think we've lost Dylan, I'm not sure why, maybe internet problems, or Jashank, unless no one seems to be chiming in with things to answer. Zach has been super busy in the chat, I can see, trying to answer questions, clarify no doubt my less than clear explanations and so on. Thank you, Zach. But unless there's anything more, we're 1 minute to go before the hour, so I'll let you go, and thanks for your attention. Thanks for your patience with listening to me try to explain this difficult topic. Next week we're back to embark onto our journey further into the machine with assembler. So I'll see you all next week for more on our journey into bits, representations, what the silicon actually does. But today you've seen what the silicon actually does with floating point numbers. See you all later.